Welcome to Innovate and React. This episode will be about the chemical reaction that feeds the world. Back in the 19th century, humanity was facing a huge problem. We were running out of nitrogen in the soil and needed to replenish it. William Crookes, a British chemist, made the projection that starvation will come due to growing population and shrinking supplies of natural nitrogen resources like guano, which were used as a fertilizer back in the days. Also, he said, chemists have to come to the rescue. But as a chemist, you might think, how can we ever run out of nitrogen, since it makes up most of the atmosphere around us? However, the nitrogen is not usable for plants to grow that way. Natural processes are slow and cannot keep up with humanity's hunger for more. There are two processes in nature who can make the nitrogen accessible. One natural way would be lightning. It provides enough energy to split the nitrogen triple bond, which is incredibly strong. In fact, so strong that it is used as an inert gas in many chemical laboratories. Another way would be biological, by some bacteria in the soil. They can actually convert this dinitrogen from the air, but this process is very slow. So we needed a much faster way that can be done in huge scales. As Crookes said, the chemists have to come for the rescue, and many tried. Already in 1811, Georg Friedrich Hildebrand tried to combine nitrogen and hydrogen under pressure to form ammonia. But he was not successful. However, he was on the right track, because pressure is one of the conditions you need for the synthesis of ammonia. About 100 years later, Fritz Haber started working on the same problem as a low-level academic at the University of Karlsruhe. His initial experiment yielded only 0.005 to 0.012% of ammonia, so very little, at atmospheric pressure and 1000 degrees Celsius, using an iron catalyst. The problem was to shift the equilibrium of the reaction, which combines 4 gas molecules into 2, so its entropy disfavored, and the reaction is exothermic. So lower temperatures should favor the ammonia yield. But at the time, they didn't have a suitable catalyst for lower temperatures. The work gained momentum when Walter Nernst challenged Haber's equilibrium data using his newly developed heat theorem, also known as the third law of thermodynamics. Nernst predicted lower ammonia yields than Haber reported, which led to a public scientific dispute. So Haber and his assistant Robert Le Rossignol went back to the lab and conducted more precise measurements at 30 atmospheres pressure and different temperatures between 700 and 974 degrees Celsius, still using iron and manganese catalysts. In 1908, their results were fully validated, and Nernst was proven wrong due to flaws in his experimental apparatus. The next option was to increase the pressure even more, as the reaction reduces the number of molecules. Inspired by observing high-pressure air liquefaction in the industry, Haber and Le Rossignol became more confident with higher pressure reactions. With the new high-pressure setup, they tested very systematically different catalyst materials from the 6th, 7th, and 8th group to lower the reaction temperature. Haber also got lucky there, because at the time he was also working as a consultant for a light bulb manufacturer. This company was testing new materials for filaments in the bulbs, and that is how Haber had access to very rare elements like osmium. In fact, so rare that in his days there were only about 100 kilograms of the refined metal in existence. he could bring a sample to his lab and tested it in his apparatus. At now 200 atmospheres and about 500 degrees Celsius, he was able to produce the first drops of ammonia. With the new catalyst, he was able to get 6% yield, a dramatic improvement from the 0.05% he started with. Now this discovery had to be commercialized. And coming back to the beginning of the story, the world was in big need for artificial nitrogen fertilizers. With further improvements, in July 1909, Haber managed to produce 500 to 600 grams of ammonia overnight, which convinced the German chemical giant BASF that the process could be promising for industrialization. That is when Haber-Bosch was tasked to scale up the synthesis to industrial scale. One key challenge was to find a cheaper and more available catalyst. Bosch immediately disapproved of osmium because of its rarity. So he sent Alvin Mittag to find a new, more abundant catalyst. To find the best catalysts, many experiments were necessary. His massive experimental campaign from 1909 contained over 20,000 experiments with all kinds of materials. To test these, over 3,000 catalyst compositions at various conditions required a new data-driven approach. His highly systematic workflow can be seen as the foundation for high-throughput experimentation and large-scale catalyst screenings that are used today. Finally, he found iron oxide catalyst, promoted by potassium oxide, calcium oxide, aluminium oxide, and silicon oxide. This recipe is still largely unchanged today, which underlies his meticulous work. The other main problem with the scaling up of the synthesis of ammonia laid in its harsh reaction conditions, which put enormous stress on the reactors, especially at that new scale. Earlier, reactors exploded or failed due to hydrogen embrittlement of the steel, which was a big problem at the used pressures and temperatures. To overcome this problem, Bosch invented a new double-tube reactor design, a breakthrough for the industrialization of ammonia synthesis. The double-tube reactor featured an inner tube, which was made of a low-carbon steel that could resist the hydrogen. This tube contained the catalyst and synthesis gas. Around it, an outer pressure-bearing steel shell. A key feature of the outer shell were small holes to avoid hydrogen accumulation that could be caused by diffusion through the inner shell. Bosch's design allowed to tame the 200 atmospheres and 500 to 600 degrees Celsius of the reaction without bursting. Only 4 years after Haber's breakthrough, BASF was able to run its first industrial scale plant in Oppau, which produced 30 to 40 tons of ammonia per day, which is again a large step compared to the 500 to 600 grams that Haber was able to make. And this new source of nitrogen, the industrial production of synthetic fertilizers, could begin, parsing the way for our current 8.2 billion population. In fact, about half of our current population is fed by crops made possible with this process. The flip side of this coin is that the Haber-Bosch process consumes a lot of energy to split the nitrogen-nitrogen triple bond and contributes about 1 to 1.8% of the global CO2 emissions. I'm not sure if this extent was foreseeable at the time, but Haber's discovery was groundbreaking. That's why he was awarded the Nobel Prize in 1918. However, his award was one of the most controversial ones, because of his role in World War I. The development of weaponized chlorine gas got him also the nickname Father of Chemical Weapons. So this begs the question if the discovery can be differentiated from the scientist. While laying the foundation for modern agriculture, supporting the billions of lives that we have today, he also made the large-scale production of explosives possible. For example, potassium nitrate can be a fertilizer and an explosive. But that's not all. Unlike other scientists, he served for his country and contributed largely to the development of chemical weapons in World War I. He claimed that many lives would be saved if the war could be ended more quickly. That's why many scientists refused to come to his Nobel lecture when Haber was given the prize, because of his involvements in the war. Nevertheless, the fixation of nitrogen from the air is one of the greatest achievements in the field of chemistry and deserves this prize. In fact, it got 2 Nobel Prizes, as Haber-Bosch also received a Nobel Prize for his contribution in the high-pressure reactor facilitating the industrial process. To me, this is truly fascinating, and as I said in previous episodes, my favorite chemical discovery. A fun fact that shows the relevance of this reaction for humanity is that about half of the nitrogen in our bodies was in the Haber-Bosch process. Next to fertilizer production and as a reactant, ammonia will also play a role for energy transport in the future energy system. As you remember from the beginning, hydrogen is used for the synthesis of ammonia. In the future energy system based on renewables, hydrogen will be a corner piece as energy storage and the bridge between molecules and electricity. Because hydrogen can be obtained from water and electricity via electrolysis. The problem is that hydrogen is not that easy to transport if not done by pipeline. So we need hydrogen carriers, and ammonia is one of them. What makes ammonia special is that it is a carbon-free alternative to all the classic energy carriers like methane or benzene we know. We already have infrastructure for ammonia in many ports, since it is traded as a commodity already. So this makes it ideal for the transport of hydrogen. To use ammonia as a hydrogen carrier, one puzzle piece is missing: ammonia crackers, the reverse reaction to split ammonia back into hydrogen and nitrogen. Currently, there are pilot plants being built to test out this new technology. Another challenge would be to find new catalysts that can withstand rapid load changes, so the synthesis can follow renewable energy supply from wind and solar. The classic Haber-Bosch process is optimized for efficiency with a constant load, ideally close to the plant's maximum capacity. This way, the maximum of ammonia can be produced, but when used as an energy carrier, it must only produce when the green electricity is abundant. With wind and solar, that can change comparably fast. So the classic Haber-Bosch process has to be newly shaped. And this is another example where old chemistry becomes relevant with new use cases and new challenges. So there's room for research, which I would like to cover in future episodes. Thank you for listening. Let me know in the comments, can the discovery be differentiated from the scientists who discovered it? Also, let me know if you like this format of the show. Don't forget to click the follow button, that really helps the show more than you think, and share this episode with your colleagues and friends. Until next time, keep innovating and stay curious.